let's look at the second part of the question. So that was the first one. The second part now is I have to calculate the velocity with which the cricket ball is bowled. Wait a minute, let me do my scenario again on my whiteboard before I say. I remember cricket ball coming towards clay, embed in the clay, and that I said was all about momentum, and I write it that way. And then they went up to a greater height, and I calculated already, and I found that the velocity here at x and there was at y. I found the following, that my velocity at x was equal to 3,13 meters. Now, what do they want to know now from me? May look at my screen again. I say calculate the velocity at which the cricket ball is bowled. Okay, so I must find the velocity of this one over here. So how do I tackle that now? By the way, I now have an answer here and an answer there. So I'm in this combination. And what is this combination about again? The conservation of momentum. Conservation of momentum. I write it like that so that I cannot forget it. So what is my approach? Let me see. What is the scenario before? Cricket ball, clay ball. Then they slam into each other, and this is the scenario afterwards. So what does the conservation momentum say? The sum of is equal to the total afterwards, and they are together, so there's nothing I can do. There's only one thing, plus nothing, so to speak, plus nothing. Okay, so there I can go, and I can start doing my sum. I write it out. I say that the momentum before, that is initial momentum, the sum of that is equal to the sum of the momentum final. And how do I write that? How many things are there? 2. So I must have 1 plus sign. 1 this side, momentum that side, 1 momentum that side. The momentum of, what am I watching now? The momentum of my cricket ball. So I will have that's the momentum of the cricket ball, all right? Let's mark the ball as number 1. Let's mark the ball number 1, and that is object number 2. So the ball is 1, and its velocity 1, and its initial velocity. That's beginning, before. And then I have my clay, and I have that as mv, but it's number 2, and that's the initial velocity of the clay. And I make it equal to one another, the one they got stuck between themselves. So it's that mass plus that mass. This is what I write, this is how I write it if they get stuck, embedded in one another. And because they are 2 in 1, it means that they have only one velocity, which I have already determined up there as 3,13. So that's no problem. Now let's see, what do I have? What other information do I have? Do I have the mass of the cricket ball? Yes, it's 0,5. Do I have the velocity of the cricket ball? No, I must find that. Do I have the mass of the clay? Yes, it's 4,5 kilograms. And I wonder if I have the velocity of the clay ball. Yes or no? Yes, I have. You know why? The clay ball was standing still. What is that velocity? It was hanging still. Velocity is 0. Do I have the mass of this one? Yes, 0,5. Do I have the mass of the clay ball? Yes, 4,5. Do I have this one? Yes, 3,13. Let me see, let me check. I've got that one, I have that one, I have that one, I have that one, I have that. I don't have that, and that's the one I must solve for. And now I go and I plug in all the relevant answers. So let's go. 0,5 times V initial of number 1. plus 4,5 times naught is naught. Oh, that's nice, huh? And then I go on and I add these together. This gives me 5. 4,5 plus 0,5 gives me 5. And I multiply that by 3,13. I think life is so good and so easy. So, if I now work out these two, I wonder what I'm going to get, but I don't worry because my calculator is at hand. So 0,5 times VI number 1 is equal to, and I quickly work that out with my calculator. I say it's 5 times 3,13, and that gives me, what do I have here now? I have a complete different answer, 3,13 times 5, and it gives me 15,65. That is how much? 15,65. Okay, so that's what I have so far. Now, just a problem. Who do I want to solve for? This one here. But he's got coupled to someone else. And how is he coupled? By a multiplication sign. So now I'm going to do the reverse on this side. By that I mean I divide it by 0,5 as long as I divide the side by 0,5. That is really what I do. So that disappears, that becomes 1. So 1 times VI is equal to that one. And that answer should give me, let me just check quickly. It looks maybe in the 30. It should be in the 30s. Divided by 0.5, it gives me 31,3. 31,3 meters per second. Okay, and there is my answer for that one. Notice how I figured out at the top what I should do. I should it out because it was a collision. Then I put down my formula and then I plugged in the numbers and I got my answer plus my unit very, very carefully. Let's look at the last question and round it off. Let me just look at it again. It says name and state the principle that you've used in answer 13,3. Come, let's look at my whiteboard again. What is the principle that I've used here? The principle of the conservation of momentum. And here I can see the momentum before, the sum of the momentum before is constant to the momentum after the collision. Okay, everybody, just a few words before we look at something else now. What I think is important that you've noticed is that we need to analyze the problem that we have. It's not difficult, not at all. In fact, most grade 12 learners should get full marks for a question like this. You just got to analyze. Now, obviously, they're never going to give you the same question in the future. But if you analyze, and I'm going to show you another problem, and then I'm going to ask you to analyze it with me, and then you are going to attempt it, and let's see whether you eventually get that answer. Are you ready? Listen, I can't work with learners who don't want marks. And learners who don't get marks don't pass. And then they got to repeat and redo it until they get it right. So why not get it right the first time around? Come, I encourage you, I motivate you, I actually ask you, I challenge you. Come and do the next one with me on the screen. We'll look at another problem very, very shortly. Let's go. Let's see whether you can find one that you can actually handle now. Okay, here goes. Watch my screen once again. Here's another challenge. Look at it quickly, analyze. I'll just tell you what is here. And thankful for all the people who are writing in today. They ask, when do you use conservation of mechanical energy? One of the answers is, can I just for a minute before we go to the challenge speak to everybody and answer one or two questions quickly? I think that will help you. Someone's asking, when do you use the conservation of mechanical energy? Basically, when you move from one point to another point. Whether it's a pendulum coming over from that point to this point to that point, it doesn't really matter. When you move away from the surface of the earth, your gravitational potential energy changes, and while it is moving, its kinetic energy also changes. So that is the reason, that's the time that you use it. So I would say, in short, anytime you move in any direction, the energy there, gravitational energy, is equal to the gravitational energy there, is equal to the gravitational energy there, is equal to the gravitational energy there, because it's actually the mgh, the height, that really matters, and not where you are. And of course, for the kinetic energy, it is your velocity. Let me look at another question. Many learners have written and very good answers, and they say, please answer, and they give me, why do you use total momentum in 13.3? Simply because there were two units in one. There was a ball, cricket ball, and there was clay, and that's why we use it. Okay, the learners ask, what's the difference between momentum and acceleration? Acceleration is defined as the rate of change of velocity, so the speed is changing. But momentum is really to see the amount of motion. That's why we take the motion, the velocity, and we multiply it by the mass. And the bigger the mass, of course, the more is the amount of motion that you have. That's why you get your momentum increasing. And so we can go on. They ask me, can't we use an equation of motion? Yes, you could possibly, but only if it is motion in a straight line. So you could probably solve the problem between the cricket ball as well as the clay. In that, you could possibly use, if you have enough information, you could use equations of motion in linear motion, or linear motion, then you could possibly use it. But when it comes to motion not in a straight line, like the pendulum swing, like the ball-clay combination going up like a pendulum, then you cannot use the, as you asked, then you cannot use the equations of motion. So please take note of that. Okay, are you ready for the second challenge? Come, let's see whether you can analyze it properly and whether you can give me the right equations, and then whether you can actually do the sum. I'm going to do as little as possible. I want you to do it this time around. Are you ready? Good. Let's see the problem itself. Right. Here we have it. A block, there's the block, 1,5 is placed on the edge of a table, 1,2 meters, and there's 1,2 meters above the floor. The block is struck by a bullet, mass so much, and the bullet is coming. Here's my bullet, and the bullet is coming this way. That's the mass of the bullet, that's the mass of the block. Now, it says here, after impact. Now, impact means when the one slams into the other. The bullet is embedded in the block, and then the block falls to the floor. So, ignore all types of friction. Analyze quickly for me, anybody. Come. Are there two situations? Yes. Here's one situation. This one comes, slam into it. Which one would that be? Conservation of momentum, of course. Which formula do I use? The bullet plus the block. Are they combined afterwards? Yes. There's my brackets. And one velocity, and then they go down. Everybody got that? Think about it. Think you got the formula. Are they separate? Yes. mv for the bullet, mv for the block. Afterwards, when the bullet reached here, they were together. The bullet was embedded in the block. So there we go. Two masses together, one velocity for the two of them. And from there to there, did the height change? Yes. When the height changes, what happens then? When the height changes, what happens then? Come on, tell me. By the way, which conservation was that one? Momentum. And this one now again will be the conservation of mechanical energy. How come I'm so sure about it? Simply because there's height involved. You see that height there? You see that height there? And there is movement involved. You see that velocity there? You see that velocity there? This is up here, and that is up there. Now, what's the velocity of this one? 0. What's the height of this one here? 1,2. Let me ask you this side. What's the height here? 0. So that all answer is going to be 0. What was the velocity here? I bet you that is what we have to find. We find the block with which the speed of 8 meters. They actually give it to us. And so, what's the first question we would like you to answer? The magnitude with which the block leaves the table. So where's that? Here, down there, which conservation do you think you're going to use? I'm not going to do the whole sum for you, but let's quickly see if we can give you some clues as to what you are supposed to be doing. Can I just hear everybody answering me? So, you must do this situation here. And can I just remind you what is the situation that you had to have? That was the situation where you must use that formula. I'm not going to do it for you. I'm going to ask you to have a look at it and quickly try and do it for me. Off you go. Try and see if you can give me that answer. I'll give it 2 minutes and then we will just look at the answers later on. Okay, so what answer did you get? Maybe we should just look at my whiteboard quickly and see if we can see what the possible answers are there. There's the answer to the first question I was just referring to. You had to try and give me the velocity of with which the block leaves the table. If you look carefully, you'll see there is the mechanical energy, right? And there's mechanical energy at B lower down. Now, if you work through it carefully, and I'm going to go into much detail, if you look at that, you have to write down your equation first, then you substitute the mass of the block plus bullet, G, the height of 1, 2, plus the kinetic energy, which is half mv squared, so it's half, plus the mass plus block and bullet, and the velocity with which it leaves the table. Then when it gets to the bottom of the table, there's no height, so it's 0, and the kinetic energy is half m, which is the total mass of the two, plus 8 squared, which is the 8 they've given us, the v squared, they've given that to us. And then you find an answer of 6,02. Okay, I will leave this on the screen at the end for you to see again. But what I want to emphasize is that you must have the correct equation, because this is conservation of mechanical energy. Substituting correctly, the possible mistakes that you could make was, one, you could have forgotten that the mass was a combination mass, block plus bullets. Again, block plus bullet, block plus bullets.